Right, good afternoon everyone. So we're introducing work energy methods today. We've gone through what has been a bit of revision about the method of joints. We introduced the force method, and we're going to use the force method to determine both the reactions, the redundant reactions, and the redundant internal forces if we have a structure that's statically indeterminate. So we'll say work energy methods. Why? So when we use the force method, and what we use it for is solving for redundant forces. In statically indeterminate structures. The key to understanding how we do the force method is that we need to determine displacements. And I'll say actually we need to determine various displacements. And I say various just to mean that we take displacements not just of the structure under load, but also we look at the displacement of the structure under, for example, under no loading and then unit loads. And later we're going to start looking at the displacement of the structure under virtual loads. So we'll just say need to determine various displacements. Now the example that we looked at, it was relatively easy to determine the displacement of the structure in the direction of the redundant force, and that's because we had a member that was perfectly aligned with them, with that side. So for some structures it's quite easy to determine any displacements under load due to the geometry, but it would be nicer if we had a simpler method. So what I'm going to do is I'm going to assume that you've gone through everything in the lectures so far, which of course you should have done. So we're going to look at the statically indeterminate structure that we looked at last time, which is an equilateral triangle. Let's pretend I've drawn that as an equilateral triangle. Subject to some loading P. Let me just check the direction I put these on. So it was A, B and C, and we've got some loading P here. So we solved this whole structure. We found that we would have a reaction of half P here, half P here, and then we had the two other reactions which were, I think, P times root 3 on 2 and P times root 3 on 2 here, and then we had the internal forces. We could have solved everything in terms of P here. Now let's consider what would actually happen to this structure under displacement. Well, we'd see probably the structure would look a little bit like this. So this is the structure with the full reaction forces. So these two nodes cannot move. We would see this node C would move to the right. It would probably also move down. I haven't drawn that very well, but because this member would be under compression, this member would be under tension, we would probably see this node move to the right. So let's say, for example, we want to work out what the displacement of this node is. Okay, and we're going to call this delta Cx. And we'll input some values. Let's say if P is equal to 150 kilonewtons, modulus of elasticity is equal to 190 gigapascals. The cross-sectional area, let's say 12 millimeters squared. And the length of all of the members is 5 meters, so that's my L there. And we know this is an equilateral triangle. What is the displacement delta Cx? So I'm going to go through now I'm going to go through and do an example using the methods that you've got so far, so not involving work and energy yet, and I'm going to fast forward through it just to show you how complicated it is to do, and then I'll also include that as a separate video if you were interested how that was done. And I'm doing this to prove a point. I'm proving that without work energy methods, this can become very, very, very complicated, even for quite a simple structure. So let's just go through how we would have solved this. So if we've got all of the loads on here, using the code that I wrote last time, and the code that we got, we can get the reactions. Using this complicated method that I'm not advising you to do, but you should sort of be happy with how it was done. We get this is 65.8 millimeters. So this is an annoying, nasty bit of algebra and trigonometry to have to do for quite a simple shape. Now, to do this on much more complicated structures, of which there are several examples in the accompanying notes, let me just think which ones we've got. For example, figure 1.10 in the accompanying notes. Have a look at that structure, and it does not lend itself anywhere nearly as easily to this sort of method as this one does, and this was difficult here. So the number 65.8, if we can get that number using a simpler method, we're going to do that. So let's introduce the idea of work and energy for this problem. So you've dealt with work and energy for dynamics before, and the concept is that the work done to a body is equal to the energy that it has. And okay, so that's the fundamental tenet for dynamics. We're going to define external work that we do to a structure, and then internal energy that's stored, and that's how we're going to apply it here. Okay, so this is our tenet. The work done by external forces has to be equal to the internal energy stored by members. Okay, so we're going to need to define what these two things are, and we will do. We'll say that the sum of external energy is equal to the sum of internal energy. Okay. So we've already said this is a sum now, so there could be more than one external forces. So if we have a structure with P forces on it, let's put uppercase P, then we simply look at the sum of the work done by all of those forces. So if we have P forces, then we just add up the external work done by all of them, and we'll do the same for members as well. So M is the uppercase M, number of members. So let's just highlight this. So we can see that we're going to have a problem here that is just some sort of external force, or a collection of external forces, and the work that they do is going to be equal to the internal energy. So we need to define these two things and how we're going to come up with some numbers for them. Okay, so remember that work is a scalar product, so it's a scalar value. It's the scalar product of force and displacement, so it's two vectors. So we're going to have a positive number for both of these. Okay, so that's what we need to determine. Let's define this. If I have my structure, and I've got force P applied to it, and we've already said the structure is going to deform to some new shape, and there is a displacement in the direction of the force, a displacement in the direction of the force, which we'll call delta. Okay, and I'm now going to call this force F for the purposes of this little exercise. Okay, it's just a placeholder, it's algebra, just a placeholder here. So the work done by this force is going to be equal to the integral of the force as it's moved through this displacement delta. Okay, so the work done by the force F is equal to the integral of the force with respect to displacement. So the external work, or the external energy, both same thing. We tend to call it external work and internal energy. Those two things are exactly the same thing. Okay, so subscript E just means external. So the external work is equal to the integral, that's the delta of that force d delta. So delta is the incremental displacement. So we need to know, we can't integrate F with respect to this displacement because F is actually a function of displacement. Because if we know that from our constitutive relationships. So if I have on here force and displacement, we know that as force increases, displacement increases linearly. Okay, F is equal to K multiplied by delta. Okay, where K is the stiffness. So you should sort of already be seeing that what we want to end up with here is the area under this curve. Okay, this is going to be our work done. Okay, so it's not simply the force multiplied by delta, it's the integral of the force through delta from the displacements from 0 up to big delta here. Okay, so since F is equal to K delta, this is equal to the integral from delta, K delta, d delta, and if we perform this integral, we end up with half F delta. Okay, maybe I've skipped a little step there, but what we would end up with is half K delta squared. We know K multiplied by the delta is simply equal to the force in the first place. Take that out and we get this value here. Okay, but this is our value, or our term for the external energy. Sorry, external work. Again, those two things are equivalent. I'll probably use those terms a little bit interchangeably. The difference that we're going to make is whether it's internal or external. So UE is equal to half multiplied by force multiplied by displacement. Okay, this is the external force. and this is the displacement in the direction of that force. And then this is 1/2 equal to 0.5. Okay, so this is our external work done. And you should see that this is always going to be a positive value, because if we have an external force on a structure, it's going to move a positive external force causes it to move a positive external displacement. Negative external force will cause it to move in a negative direction, and then in the coordinate system that would be a negative number. So this will always give us a positive number. And we can always just remember that U by definition is equal to a force by a displacement. And if these two are vectors, then we've got a scalar product. Okay, so we're always going to get a scalar out of this. So this is the external work done. If we've got more than one force on a structure, then the total external work is just the sum of 1/2 multiplied by each force multiplied by each displacement in the direction of that force. Got to be careful that we're always getting the marrying up displacements with each other. So for example, if we had a structure that looked like this, had two supports, and I applied P1 and P2, then the displacements we'd be looking for would be delta 1 going downwards, delta 2 going to the right. So for this structure, the total external work would be equal to 1/2 multiplied by P1 multiplied by delta 1 plus P2 multiplied by delta 2. Pretty easy. Okay, so we've got this idea of how we determine external work, and probably what I'm hoping you guys are seeing is that once we actually set this equation up, we do UE is equal to the internal energy. We're going to be solving for these numbers, which are the displacements we want to get. So for our structure here, that delta is what we wanted to know, because we said right back here on the previous slide, let's say we want to find this out, and then we did this the long-winded method and found we got 65.8 millimeters. So we've defined this side of things. Let's put a big ring around this. So I've got this idea of external work done. Now we need to have a look at what external energy is. So it's pretty simple. Internal energy is stored as strain energy. So for our truss structure, which is comprised of two force members, we have members that are capable of being in tension or in compression. So we tend to use lowercase f's to describe a member that's in tension. This member would extend. So if it has original length L, it's going to end up extending by some amount delta L. So the change here, it's going to be kind of hard to draw, but let's draw it like this. This would be L plus delta L. Okay, so delta L is the change. And through a very similar means that we did for external work done, we can say UI is equal to the integral of that force all the way up to delta L with respect to d, let's call it d delta. Okay, and very similarly, we'll just say again that force is actually a function of delta. So force is equal to k delta, and therefore this is then equal to the integral of k delta d delta. And hopefully you'll see this just gives me a half force multiplied by dl. So this is telling me that I should have done this in green, shouldn't I? Bummer. I'll start doing it in green now. So this is telling me that my internal energy in a single member is equal to 1/2 multiplied by the internal force in that member Remember, this is a vector, so this can be positive if it's in tension, negative if it's in compression, if that's the sign convention you're using, multiplied by the change in length. And again, this is also a vector, so this can be positive if it's extending, negative if it's in compression, and that's if you're using the same sign convention here. So because we've got two vectors multiplied as the vector product, we end up with a scalar, which is simply the internal energy. So again, this is just a number, can only ever be a positive number. So this would be for a single member, and hopefully what you guys will see is that if we want to look at the total internal energy in a structure, we just do this for every member and we add it up. This is for a single member. For the whole structure, we just add it up. Okay, so I'll write that down as well. Let's just say that for the sum of internal energy is equal to the sum over m members with lowercase m equal to 1 half the force on that member multiplied by the change in length of that member. Okay, and again, half is equal to 8 divided by 4. Okay, so we've defined these quantities now. We defined what internal energy is and what internal energy and external work done is. These two things are going to be equal to each other, and the only thing we don't know at this point is these external deflections. So we can solve for that. So going back to this problem here, let's look at the problem that so again, I've already got the answer to this because I went through the complicated way. Let's just check if this adds up on this structure. So what is our internal energy for this structure? This structure is really easy, so this is good. So we can see that like any other structure, the sum of internal energy is going to be equal to the sum of all of those forces and multiplied by the deflections. So we'll say that's equal to 1/2 multiplied by F AB multiplied by delta L AB plus a half FAC multiplied by DL AC plus a half FCB multiplied by the change in length along CB. Now up here we worked out these forces, and this was from last week or from the video that you probably watched 10 minutes ago. FAC is just equal to minus FCB, and the according lengths are just going to be the same, but minus one is equal to minus the other. And FAB is equal to 0, so I can actually just modify this. I can say, okay, it's going to be that is equal to 0. I can get rid of one of these and get rid of the half sign here. Because it's a scalar product, because we've got the same magnitude of force and the same magnitude of displacement, the same internal energy will be stored in both of those two members. So for our problem, that is, the internal force was 150 kilonewtons multiplied by the extension, which is 0.0324. So that's going to be 100, oh no, calculator's in the wrong mode. I don't think I've ever used it in stats mode. 150 times 10 to the 3 multiplied by 0.0324 gives me 4.86 kilojoules. This is the internal energy stored within the structure, and it has to be equal to the external work done. So if this is my structure here, there's only one node that can move, and there's only one displacement in the direction of that external force. So my external work done is equal to half P delta Cx. And delta Cx is the bit we want to find out, and P was just 150 kilonewtons. So the external energy is equal to a half multiplied by 150, so let's call it 75 kilonewtons multiplied by delta Cx. Don't know why I put the units in there, that was a little bit silly. That's got to be equal to 4860. So delta Cx has got to be equal to 4860 divided by 75,000. I hope this is right now. And what do we get? Close enough, pretty much. Yeah, okay, so we get, yeah, I get 64.8 here. And doing it the long-winded way, I got 65.8. I think I must have made a mistake in one of these numbers somewhere. What I'll do is I'll attach the accompanying update to the Jupyter Notebook. So I've done this with the Jupyter Notebook, and I've shown that we get 65.8 both ways. I think I must have calculated one of the, let's have a look. I must have calculated one of these external energies slightly wrong, I think. Oh, it's because these extensions are incorrect here. These extensions are incorrect. These should be 0.0329. I've messed up one of the digits here, okay? But again, I'll just attach the updated Jupyter Notebook that goes through the previous example and just works out the internal energy, equates it to the internal energy, and then solves for this deflection. Now, I hope you guys see that that's a much easier way to solve for deflections in a structure. And when we go on to look at structures like the figure 1.10, then we're really going to need to use this method because it helps us to solve for deflections. What we're going to see next lecture, I'm going to go through another example of this. We'll see that actually this is powerful. And it's powerful, like I say, it's powerful because we reduce the problem to a scalar problem. We take the geometry out of the problem. The geometry is handled by the force method, sorry, by the method of joints. Okay, so all of the geometry information is contained within the method of joints, and then we've just got this scalar quantity work to equate, and then we can get the answer out. Now, this is fine, when we've got a force working in the direction that we want to know a displacement of. So when we don't have that, we're going to need to invent one. And that's where we introduce this idea of virtual forces, and that's what the next couple of lectures are going to be about, using the principle of virtual displacements. So let me just have a look at the accompanying notes. There is a full example of work energy methods. So there's a good write-up of work energy methods and how they work. I would like you guys to read through the accompanying notes on work energy. I go into it in quite a lot more detail in there. I've given you a good top-level introduction. Let me just have a look. No, I'll leave it here. I'll leave it here. So go through the notes, read up to section 1.3.3. So by this point, I would expect you in the module 2 accompanying notes to be read up to the end of page 22. Okay, and then we're going to start doing some more examples, and we're going to be using, okay. In fact, sorry, not up to page 22, go up to page 27. Okay, I want you to go up to page 27, go through it and understand the problems that are there within. Okay, and then we're going to introduce this idea of virtual work next lecture. So that was a quick intro to work energy. I hope you see that it's a powerful method to solve displacements in structures, and I hope you've enjoyed it. I'll see you all probably some point later this week. I'll be recording more of these this week, and this module is a good one. It won't be I don't think it's quite as difficult as the last one, but it's conceptually quite difficult to get your head around this idea of using internal energy and then these idea of virtual forces. That's going to confuse a few of you, but hopefully it'll suddenly click and you'll think, yeah, I understand that now. So have a wonderful whatever you're doing, and I'll see you guys all soon. Take care. We had the reactions for this would have been the FBX is equal to FBA is equal to minus 75 kilonewtons, and the other reaction would have been FAY would be minus 129.90 kilonewtons, and FBY is equal to 129.90 kilonewtons. So you guys should be able to do this, okay? This is using the code we wrote last time, the equations that we wrote last time. We could also get all of the internal forces. So the internal forces, we'd have FAB, FAC, and FCB. Those are all the internal forces which we solved as a function of these. And the internal forces would be, well, FAB is actually a zero force member. So that's 0. FAC is 150 kilonewtons. And then FCB is 150 kilonewtons. Is a minus 150 kilonewtons, sorry. Okay, so we've got the total forces present in the structure. Let me just check one of those numbers because I want to check I'm using the right version of this code. Yes, those are fine. Those numbers are fine. I'm just checking I'm using the right version and going back through the notes. So these would be our internal forces in each of these structures. Now what we're trying to determine is this displacement up here. We can, based upon these, all of the internal forces, we can say that member AC, which is going here, is in tension, so it's going to get slightly longer. And remember, CB is under compression, so it's going to get slightly shorter. And remember, AB hasn't got any force on it, so nothing's going to happen. So we can use the expression delta L is equal to F multiplied by L on EA. Okay, so that gives us the force, sorry, the extension or contraction within a member. And we can work out, based upon these two forces we've got here, we can see that one's going to contract by the amount that the other would contract by. So let's just get those numbers, because I did this example earlier. I want to just check I've got all of the numbers written down. Okay, so this one doesn't extend or contract. This one extends by 0.0324 millimeters. Sorry, meters. And this one is going to go the other way. Okay, so remember, AC is under tension, so it gets longer. BC is under compression, so it gets shorter. Now we want to work out how much this node moves to the right. Now this is just a nasty bit of geometry. It took me a little while to figure out how to do this. So if we've got our original structure here, and it moves to a deformed structure here, then we've got some angles in here that will help us. The angle that's going to help us is this one here, which I'm going to call alpha. Okay, that's the angle. So we've pulled on it, the structure's moved to alpha. And we can see that what we've got is a triangle that's composed of two right angle triangles here. Okay, so the amounts, this length here, okay, let's call this L prime. In the original structure, this would have been half of the base, okay? So whatever this distance is, minus half of the original base, is the amount that shifts to the right. And again, we're only doing this to show how we get the number, and we're going to show that it's much, much easier with work energy methods. So we can use the cosine rule to determine the angle alpha here. Remember the cosine rule, if we've got a triangle like this with A, B, C, C, A, and B, then A squared is equal to B squared plus C squared minus 2 BC cos A. So we can use this rule to get alpha, knowing that this would be just all of these sides would be equal to the 5 meter length plus or minus, or just add on these two numbers here, and the bottom one doesn't change length at all. So we can work all of those out. You get the angle is equal to just slightly smaller than 60 degrees, which is good because that's what we would expect. And then we would get that using this method,